right, let's get started. So hi everyone, this is Ruijie from UIC, and today I'm very glad to be the first in-person author in this session. And today I'm going to introduce our SIGIR paper titled TGOnline, Enhancing Temporal Graph Learning with Adaptive Online Method Learning. And this is a joint work with UIC, Zhejiang University, Stanford University, and Shanghai Jinyang University. I will start by introducing some background. The knowledge graph is a ubiquitous data structure widely utilizing in many real-world applications. For example, they are widely utilized to describe users' online time-step behavior on X, Wikipedia, Yelp, and Reddit online platform. And it can be viewed as a set of temporal edges, including a source node, target node, and the associated time-step. And they are collected in a streaming manner. So temporal link prediction is an important task on the temporal graph to illustrate how well the representation learning is modeled. Specifically, it aims to predict the missing source or target nodes in the triple. And we can see from this two running example collected from Reddit and Twitter, the large volume of temporal edges are collected in a streaming manner. One consequence of that streaming data collection is that we observe the new edges and the new nodes are continuously emerging over time. As shown in the two figures below in the left side, this leads to a significant performance drop for the deployed model online because the old model cannot capture the updated information presented in the new node and the new edges. So the link prediction model needs periodical updates online during online phase to maintain sentence performance over time. To be concrete, in this paper, we study a task called online learning on temporal graph. Specifically, during the offline phase, we can train our model on the pre-collected data. And then we deploy it online to serve it in different collection periods. And at the end of each data collection period, we can retrain or update our model by the most recent collected temporal edges. So in this paper, we developed a temporal graph learning technique that can facilitate the effective and efficient online updates, boosting the downstream applications in the streaming scenario. There exists some naive strategies. For example, the direct inference that's directly utilizing the old model parameter on the new data. But apparently, it is a suboptimal solution. And also, the online fine-tuning or the full-time retraining is unsatisfying because the former one easily causes the overfitting and forgetting problem on the exclusively on the new data, while the latter one, the retraining, is expensive and the process will be likely dominated by the large volume of existing data and therefore ignores information from the new data. Our hypothesis here is that we can view the task on different, the learning task on different time steps as a similar and task, so that we can extract some generalizable knowledge across tasks in the consecutive time step. And then during the online phase, once we collect the new data, we can largely inherit the global parameters from the old data and just perform some regularized lightweight fine-tuning. And it turns out that our approach not only achieved the best online serving performance, but also achieved the shortest update time. So towards this goal, there's still two challenges remaining. The first is, as we all know, the graph learning model, especially for the temporal graph learning model, tends to be sophisticated, especially compared with the naive GCN. So how can we distill the enduringly valuable knowledge from the global parameter at each new time step? And the second challenge is, considering the frequent data collection, we need to further accelerate the online model updates to reduce the time and the energy consumption. So how do we achieve this? I would first to introduce the backbone model we use in this paper. It's called TGAT, which aims to sample and aggregate the information from temporal neighbors. The high-level intuition behind is that the dynamic of the representation vectors of each node is caused by the changes of temporal neighbors that they interacted in the recent time step. So the backbone first sample a dynamic temporal neighborhood set from multi-hop neighbors. And then it utilizing the attentive aggregation from the temporal domain to aggregate the information from their neighbors. And the corresponding aggregation attention weight calculation is shown in the equation on the right. So recall that the first challenge is we need to extract some enduring or temporally robust knowledge from the global parameter. How do we tackle that? We propose a distillation-guided fine-tuning. As we can say, instead of directly optimizing the loss on the new data, as shown in the first term on the right side, we propose a fine-tuning objective that consists of two parts. The first is just the loss on the new data, but we also enhance it with regularization between the updated parameter and the global parameter. Intuitively, it guarantees that the updated parameter is not that different from the global parameter, so that it can inherit some valuable knowledge from the global parameter. And also, which part of a parameter will be inherited and which part will be optimized can be fully determined by a data-driven process. The next question is how can we ensure and enhance the generalization of the global knowledge? So we formulate it as a meta-optimization problem, where we view the representation learning at each time step as a task, which aim to adapt the global parameterized initialization on the recent collected new data to update the model for future link prediction. So correspondingly, the optimization can be viewed as a bi-level optimization, and they are next to each other, similar to the model agnostic meta-learning. Where the inner loop optimization mimics the online fine-tuning process, which inherits the global parameter as a model initialization and performs the aforementioned distillation-guided fine-tuning. And here, how can we quantitatively measure the quality of global parameters inherited from the other time step? We utilizing the future link prediction performance to reflect how well the initialization is. So we correspondingly utilizing the outer loop optimization to iteratively improve the quality of global knowledge. And the second question is giving the meta-learning to guarantee the generalization of global parameter and the distillation fine-tuning to guarantee and avoid the overfitting problem, how can we further accelerate the online model updates process? Here we first propose a technique called edge reduction. Basically, we find the time complexity of online fine-tuning grows linearly with respect to the newly collected temporal edges. And, but we find that not all the temporal edges can bring in new information because some of them already be encoded in the old global parameter. Empirically, we find that by removing edge between two hop neighbors in recent 2 or 3 time steps, we can accelerate the whole process by half, but do not observe the significant performance drop. For example, in this example, we can, the new edges between node 2 and node 4 at time step T2 is skipped as it connects two nodes, 2 and the second and the fourth nodes within the 2 hop neighbors in previous time step. And also, we find that during the online updating process, a repeated query to query the node representation at a certain time is happening for multiple times, which means the same node and time query pairs appear in batches for multiple times. One quick solution for that is we can cache the calculated time, the node representation at a certain time, so that once the model needs to query the same node and time pairs, we can directly create from the cache, not by the forward pass. As an example, in this case, we find the node computation that query the first node's representation at the first time step is removed because of the duplication. And after the publish of this paper, we further integrate our code with the two famous efficient temporal graph learning framework called the TGOBK and the TGLite. Now later, we can see ours is compatible with these two famous framework, and it can bring in extra speed up. Okay, let's move to the experiment part. We evaluate our model on 4 datasets, including the wiki, Reddit, Twitter, and Yelp. Basically, they are all the dynamic bipartite graph describing the user and item interaction over time. And we utilizing the ranking-based metric recall and NDCG to evaluate our model and compare the major recent state-of-the-art baselines from static graph learning, dynamic graph learning, and online graph updating categories. First, we find that compared with around 18, I think, baselines, ours can achieve the consistent improvement and bring in about 88% of the relative gains. And as for the detailed performance improvement, we quantify the performance improvement with respect to different node groups, from the node group Q1, denoting the most inactive nodes, and the Q4, denoting the most active new nodes. And we find the larger improvement mainly comes from the inactive groups, illustrating by utilizing our distillation-based fine-tuning, ours can achieve a good generation ability across the inactive nodes and the active nodes. Further, we find that compared with the naive retraining and fine-tuning, ours can achieve the best performance and also the shortest updating time, especially compared with the naive fine-tuning, because we use the edge reduction and the node deduplication technique to further accelerate the underlying computation. And compared with other optimization method, ours also achieve the best performance. Here is the efficiency evaluation. It's a large table. Let me introduce it one by one. First, we illustrate that ours, as I said, is faster than retraining and fine-tuning technique. And also, if we look at the fifth row, we find that the edge reduction technique can bring in about 2 times speed up. But it only leads to about 1% of performance drop. And further, if we compare the last two columns, called the TGOPK and the TGLite, we find that our model is kind of compatible with these two famous library, and each integration can bring in extra speed up from 1 time to 2 times speed up. And here is the takeaway of our paper. First, we study an online learning problem on the temporal graphs, and we propose a TGOnline framework. And the high-level intuition is that we can largely inherit the old parameter and utilizing the regularization-based fine-tuning on the new data to achieve both the predictive performance and efficiency performance. And further, we show that it is compatible with the TGOPK and TGLite, and it can bring extra speed up. And I think I will just stop here, and I'm glad to take any questions from the audience.